Well, students, this is 17th lecture in the series of mechanics of metal forming. Recall back the earlier lecture where a set of 3 lectures rather, where we discuss the yield criteria, different yield criteria for tropic material basically. So there was no any anisotropy in those materials. We discussed 3 different criteria like von Mises yield criteria, Tresca yield criteria and Hill's criteria. That was all related for isotropic material. But you know, a material after deformation, even if you start with a very pure isotropic material, after deformation little bit anisotropy is also developed. So one can see that most of the metals exhibit anisotropy either to a small level or to a larger level after the plastic deformation is taken place. That is, the mechanical properties of the metals vary in different directions. If there are 3 directions in case of 3-dimensional case, 2 direction in case of 2, so it changes. The amount of anisotropy is a characteristic of the material and also the heat treatment which is done on after the processing and which is subjected in previous processing as well. So for an example, a sheet metal which has been very severely cold worked in cold rolling, for an example, if one can see here in figure number 1, once it passes a significant orientation of the crystal as discussed previously, the crystal structure which cannot be removed by annealing, because whatever crystal structure has been created after deformation, annealing will not be able to remove that. So the yield stress which is obtained from the specimen, which is after the cutting from such cold rolled sheet at various angles, generally 0 degree, 45 degree and 90 degree was preferred to the direction of rolling, will therefore exhibit significantly different values at the same total plastic strain. Similarly, the yield stress in the thickness direction may also be significantly different. If you look at this figure number 1 here, where the conventional direction in sheet rolling has been shown, the variation in these yield stress values may not be more than 15%, it has been seen, and for most application the material may be considered to be isotropic. However, in certain operations like deep drying, the quality of the final product is significantly dependent on the degree of the anisotropy present because of the deformation. It is therefore necessary to develop a theory to predict the important features of plastic flow when there is anisotropy present, either because of the previous operation or because of the deformation. So for these cases we must have another yield criteria which incorporates anisotropy, that would be better, and that planar anisotropy which describes the variation of mechanical properties in the plane of sheet and characterized by the amount of easing that occur when drying a cylindrical cup from a flat circular blank, one can see. And normal anisotropy describes the strength of the metal through the thickness of sheet, which is relative to its strength in the plane of sheet. So, with this introduction, let us see anisotropy yield criteria. So, as in orthographic anisotropy, there are three mutually perpendicular planes of symmetry at every point, and intersection of these planes are is known as the principal axis of anisotropy. So, the along this and along this would become the principal axis of anisotropy. So, taking the principal axis of anisotropy as the rectangular Cartesian coordinate system, the yield function in deuteric stress space can then be a surface, as it is shown in figure number 2 here, if one can see. So, assuming the yield function, let us assume this yield function as shown here in equation number 1, which is f, and this is given by say capital C ij k h sigma ij sigma k h minus 1 is equal to 0. So, for this is what is the, and let us start with the anisotropic yield function as shown in equation number 1. If you see this particular constant C I J K H, so C J K I J K and H in the notation of tensor, each has got 1, 2, 3. So, that means 9 multiplied by 9, it is total 81 anisotropic parameters. Ijkl are functions of current state of stress and strain, and therefore, if you recall the flow rule, which is one can determine the strain increment tensor equal to d lambda multiplied by deva f by deva sigma ij, where f is the function which is shown here, anisotropic function as shown in equation number 1. So, this if you substitute the f, one can get the equation as shown in 2, which is d epsilon ij would be equal to d lambda C I J K L and sigma k h. Here I J K H, there are 81 independent constants, can be reduced by imposing the following restrictions. So, if we assume certain restriction, so restriction number 1 that we can take when the symmetry of the stress tensor is taken as, that means sigma kh must be equal to khk, and therefore Cijkh can be written as Cijk Ijhk. So, because of the symmetry. Secondly, the symmetry of the plastic strain increment tensor gives what? So, that means that d epsilon ij would be equal to, would be taken as equal as the d epsilon ji, where Cijkh, because it can be written as previously say Cjikh, and third, which we can assume that the plastic strain increment gives therefore dw, that is work done, which is equal to sigma ij multiplied by d epsilon ij, and that becomes equal to d lambda C ij multiplied by sigma ij sigma k, because dw is a scalar quantity and ij k h are dummy suffix as explained in tensor notation. So, Cijkh is equal to Ckhij. So, these three assumptions as a restriction will reduce the independent parameter, which was 81 in equation number 1 to 21 only. If you remove all these three assumptions restrictions and put together. The fourth assumption, it is that there exists three principal axes of anisotropic. That indicates that the direct increment are independent of the shear stresses and the shear strain increments are independent of the direct stresses, and thirdly the shear strain increments are functions of the corresponding shear stresses only. That is, we can say that d, for an example, d epsilon 11, that is the shear increment, direct strain increment 11 can be written as C 1111 sigma 11 plus C 1112 sigma 12 plus and so on plus C 1122 sigma 22 plus dot plus C 1133 sigma 33 plus and so on like that. So, this, if you see the equation number 2 and if we incorporate the assumptions which we have just now seen, the fourth assumption especially and the first part of the fourth assumption, it follows that the terms such as C1112 etc. are identically 0 in fact. So, similarly the shear strain increments can be put together, that means d epsilon 12 can be written as d lambda in bracket C 1211 sigma 11 plus C 1212 sigma 12 plus etc. dot plus C 1213 sigma 13 plus and so on. And if you look the assumption in second part will give the coefficient, that is C1211 etc. as identically 0 value. And also the assumption, the third assumption in part 4 will give coefficient such as C1213 as equal to 0. The only non-zero coefficients are therefore C1212 like C2323, C3131, and only therefore 9 independent isotropic parameters will remain. And therefore, now if you put together the anisotropy condition, that is d epsilon I is equal to 0, sum of the direct strain increments, sum of those is 0. So, if you substitute this will give that C1111 sigma 11 plus C2222 sigma 22 plus C3333 sigma 33 plus C1122 in bracket C11 plus sigma 11 plus sigma 22 plus C2233 in bracket sigma 22 plus sigma 33 plus C3311 in bracket sigma 33 plus sigma 11, and this all sum, that is almost 9 components, the sum of these would be equal to 0. And this condition particularly will only be satisfied if C1122 is equal to minus half of C1111 plus C2222 plus C3333, and C2223 becomes equal to minus half of the C222 plus C3333, C1111, and C3311 becomes equal to minus half of the corresponding in the similar manner components like C3333 plus C1111 plus C2222. This is evidently true when sigma 11 is equal to sigma 22, sigma 33, and that is all equal to sigma. In this equation, if this three set of equation is satisfied, then only 6 independent coefficient of the anisotropy will remain, and this is what is shown here as a form of array. So, this array one can see here, that is C1111, C1112, C1133, C11111, C1122, C1133, C1111, C1122, C1133, and the diagonal terms if you extend on this side, that is C2323, C3131, C1212, and all other terms are 0, and therefore it is not shown here. So, if you look at this the principal axis concerning the anisotropy, it looks like as shown in 3 here. So, one can see here there are x, z direction and y is along here, and if theta is the angle with the change position of the axis, say x1 and y1, and so this kind of defining anisotropy, it was first given by Hill, R. Hill particularly in 1948, and therefore the name is called as the Hill yield criteria for anisotropic material, and it uses 6 independent coefficient of the anisotropy. Therefore, Hill assumed that the material has 3 mutually orthographic principal axes of anisotropy, which is normal to the corresponding planes of symmetry, and therefore the Hill proposed the yield function as shown here in equation number 3. So, if you see the equation number 3, it looks like here 2f, that is the twice multiplied by the function yield function, Hill's yield function in terms of the sigma ij tensor, and that becomes equation number 3. So, you will see that here are f, g, h and I and L, M, N, these are the constants. These constants are determined experimentally. Lot of experiments are to be done in different directions, keeping and deformation in a plane, and so lot of experiments are carried out, and then the value of f, g, h, L, M, N are calculated, and if you substitute here, and then this is what is the popular yield function which Hill proposed in 1948. So, as I told you, the f, g, h, L, M, N are the parameters which are characteristics of the current state of anisotropy. These constants can be evaluated, as I told, lot of experiments are to be done. These experiments can be simple tensile, it can be pure shear tests, and in 3 mutually perpendicular directions. If suppose capital X, capital Y and capital Z are taken as the yield stresses, in simple tension along the x, y, z directions. And if you look the figure number 3 here, so one can write down 1 by capital X square is equal to G plus H, 1 by capital Y square is equal to H plus H, and 1 by Z square is equal to F plus G, and this has been shown here, this set of equations in equation number 4. So from the above expression 4, one can find out that if you manipulate these 3 equations, one can get that capital 2F becomes equal to 1 by y square plus 1 by z square minus 1 by x square. And similarly, the 2G would be equal to 1 by z square plus 1 by x square minus 1 by y square. 2H can be equal to 1 by x square plus 1 by y square minus 1 by z square. And likewise, for the pure shear case, that corresponds to the L, M and N, one can do the pure shear test and one can get the equation like 2L is equal to 1 by R square, 2M is equal to 1 by S square, and 2N is equal to 1 by T square, where R, S, T are the yield stress value in different planes like Y, Z, X, Z, X, Y and X, Z direction in planes. So for a complete isotropic material, therefore, now if you see the whatever we are going to propose, what was proposed by Hill, one can get the isotropic situation as well. If you substitute these terms to be 0, that means for getting a complete isotropic, that means capital X, capital Y, capital Z, it must be all equal to the yield stress, that is sigma, and that is the tensile tension part, and the shear part, that means capital R, capital S and capital T, it must be equal to the shear strength of the material, that is small k. So one can then say from the equation number 5, 6 and 7 that capital F in simple isotropic, therefore it can be said that when x, y, z is sigma and r, s, t are equal to shear component, then capital F, capital Y, capital H are all equal, and it would be given as 1 by twice sigma square, and capital L, capital M, capital N likewise would be equal to 1 by twice k square. The von Mises yield criteria, therefore, for isotropic material, which was previously discussed, gives the value k, that is the shear part, which is equal to sigma by root 3, and therefore capital L is equal to capital M is equal to capital N, and it is equal to 3F, it is again equal to 3G, and it is again equal to 3H, and this is all equal to 3 by 2 sigma square. This is shown in equation number 10 here. So if we substitute these in the anisotropy yield criteria, which is given in equation number 3, and one can get the final equation, which is the von Mises yield criteria for isotropic material previously which was given. So this gives your sigma xx minus sigma yy square plus sigma yy minus sigma zz square plus sigma zz minus sigma xx square plus 6 of the shear component summation of all those with the square, and that is equal to 2 sigma square, and this is what the von Mises yield criteria for isotropic material has been. So that is now proved. So that means Hill's criteria is correct, and even we can derive the situation for the criteria. Now let us see the flow rule concerning anisotropic Hill's anisotropic criteria. So what should be the flow rule corresponding to that? So as the flow rule, a plastic, that means plastic stress strain relation can be directly used to using the plastic potential concept. So we use the plastic potential function G sigma ij, and it was said that one can derive the plastic strain increment from this function, and it can be obtained by partially differentiating the G function G with respect to the tensor, that is sigma ij, and this is what is shown again here in equation number 12. So the negative value of d lambda would mean a negative strain associated with a positive stress. The above definition, that is in equation 12 of the plastic strain increment, now it can be more general, it can be generalized and can be called as the non-associated flow rule, because d epsilon ij, the increment of the strain tensor, is not associated with the yield function f now. So but in case when the function g and f is equal, so it will lead to the associated flow rule therefore. So if you substitute the g and f together, the Hill criteria, which is shown in equation number 3, it will give this equation, which is equal to 2f sigma ij, and it is equal to the right hand side where there are 4 terms. So the first term, which is capital F sigma yy minus sigma xx square, plus second term as capital G sigma zz minus sigma xx square, and third term capital H sigma xx minus sigma yy square, plus fourth term as altogether 2l sigma yz square plus 2m sigma xx square plus zx square plus 2n sigma xy square and minus 1, it should all be equal to 0, and this what it gives the value, which is deva f by deva sigma xx, it becomes as shown in 13 equation. So this becomes equal to g sigma xx minus sigma zz plus capital H sigma xx minus sigma yy, and therefore one can get the plastic strain increment in xx direction as shown here in equation number 14. So and similarly one can get in the yy direction the strain increment as shown, and this is what is being shown here in equation 15. So and likewise the z increment, strain increment can be, and it is for the ease it is shown in equation number 17. That, and also if you recall d for the shear part as well, so it can be written as d deva f divided by deva sigma xy, and it will be equal to capital N sigma xy, which is shown in 17. And likewise one can calculate from equation number 17 that d epsilon xy is equal to d lambda capital N sigma xy, and that is equal to d lambda capital A xy, and similarly the other shear component increment can be calculated, that is in yz plane and zx plane, and this is what is being shown in equation number 19 and 20. Now if you put all these together, because it is all equal to d lambda multiplied by the associated things, so one can write down the associated flow rule to the Hill's anisotropic criteria as This is shown in here in equation number 21. So that would become d epsilon xx divided by capital A xx, and this is equal to d epsilon yy divided by capital A y, and this is again equal to d epsilon zz divided by capital A zz, and this is equal to d epsilon xy, which is divided by capital X A xy, and it is equal to d epsilon yz divided by capital A yz, and it is d epsilon zx is equal to capital A zx, and this is what is equal to d lambda. So this is all together has been shown, which is in equation number 21, where if you see here in equation number 18, 19 and 20, capital A xx, capital A yy, capital A zx, capital A xy, this is all equal to these terms. These are shown. For an example, capital A xx is equal to capital H multiplied by sigma xx minus sigma yy plus capital G sigma xx minus sigma zz, and likewise say capital A xy is equal to capital N sigma xy capital A yz, and that is equal to capital L sigma yz A zx, and that is equal to capital M. So this can be so the generalized associated flow rule becomes for anisotropic material as shown in equation 21. Now we can use this generalized flow associated flow rule for the anisotropic case to let us have the generalized stress and strain, and so that it can be used for most of the analysis purpose. So as we recall the generalized stress as sigma bar and generalized strain as strain increment as d epsilon bar, and then one can write down, if you recall earlier from the earlier, so it is again to put it here in equation 22. So that is dW, that is the incremental work done is given by the generalized stress multiplied by the generalized strain increment, and it can be put together in the tensor form, which is shown here in equation 22. So and if we use equation number 14 to 15, one can write down by substituting here the generalized so these are can be from the equation 14 to 15, one can write down that capital F multiplied d epsilon xx, it becomes equal to d lambda, and the two terms inside, that is F capital H multiplied by sigma xx minus sigma yy plus capital G capital F multiplied by in bracket sigma xx minus sigma zz. The strain increment yy and terms associated with and strain increment zz can be written. These all three set of equation is shown here in equation number 23, and therefore one can manipulate the equation number 23 and it can be further written in another format, which is shown here in 24, equation number 24. And let us take that Q is taken as the sum of capital F G plus capital G capital H and plus capital H capital F, if it is taken as the sum of all these things. So this equation number 24 can be written here in the, which is the set of three equation again, and it is equation number 25 shown. So this states that capital H multiplied by, that is capital F, and the strain increment in x strain increment in y direction, and this whole together is square. On the right hand side it becomes q square. Q is the addition of those terms, three terms. So q square d lambda square capital H and in bracket sigma xx minus sigma y square. And this is likewise we can extend it for the other strain components, strain increment components, and this is all has been shown in 25. Now using this 25, equation number 25, one can write down that capital F by capital Q square and in bracket capital G d epsilon yy minus h d epsilon z the whole square plus capital G divided by Q square plus this term, and this is all shown, that is the 3, 4, 5 on the left side. This particular equation is shown here in 26. So the equation number 26 has got on the left hand side it has 4 terms, and on the left hand side it is again 4 terms. So this, what is, if you substitute the equation number 25, if you substitute the values, and then one can get here the equation number 26. This equation therefore uses the equations which are substituted from equation number 18 to 20, and therefore it gives that d epsilon yz square is equal to d lambda square capital L square and sigma yz square, etc., and likewise all other terms. So using the previous equation 3, that is was the flow rule, the right hand side of the equation number 26 can be written and it can be equated to d lambda square, and therefore let us see this equation number 27. If you substitute this one, so it becomes capital F by capital Q square, and in bracket, that is the first term as capital G d epsilon yy minus h d epsilon zz whole square plus second term as capital G by Q square, and in bracket it is capital H d epsilon zz minus f d epsilon xs square plus capital H by Q square, and in bracket capital F d epsilon xx minus g d epsilon yy the whole square, and that is plus 2 by capital L d epsilon yz square plus capital 2 by capital M, that is 2 by capital M d epsilon zx square plus, that is the shear components, 2 divided by capital N d epsilon xy square, and all these together if you take the under root it would be equal to d lambda square, and this is what complete equation has been shown here in equation number 27. These substitution must be very carefully seen, because anywhere if these values are discarded or left out, then the whole thing will be disturbed. So now we can write down the generalized yield stress, that is sigma bar, and the generalized strain increment, that is epsilon bar, and it can be written as the work done, the work which is equal to sigma bar multiplied by d epsilon bar, and that is in the tensor form it is equal to sigma ij d epsilon ij, and that would simply be given as sigma ij multiplied by d lambda and deva f by deva sigma ij, and this is what is shown in equation number 28. This is the equation. So here on the right side of the equation 28, if it is seen, so we need to calculate sigma ij and deva f by deva sigma ij. So if you substitute, if we evaluate these things, we can get the values accordingly, and this is what we get in equation number 29. So that means it becomes the different terms like sigma xx term, sigma yy term, sigma zz term, and the shear terms, the shear stress term. So for an example, sigma xx on the left hand side, deva f by deva sigma xx, it becomes equal to capital G sigma xx square minus sigma xx sigma zz plus capital H sigma xx square minus sigma zz sigma yy, and secondly similarly sigma yy deva f by deva sigma yy becomes this one, that is capital F sigma yy square minus sigma yy sigma zz plus capital H sigma yy square minus sigma xx sigma yy, and sigma zz multiplied by sigma zz is equal to capital G sigma zz square minus sigma xx sigma zz plus capital F sigma y square zz minus sigma yy sigma zz, and the shear part similarly can be evaluated as sigma xy deva f by sigma deva f by sigma xy, which is equal to capital N sigma xy square, and sigma yz multiplied by deva f by sigma yz is equal to capital L sigma yz is yx square, and sigma zx multiplied by deva f by deva corresponding sigma zx, it will be equal to capital M and sigma zx square. So if we add these 6 equations all together, it will give, which is shown here in equation number 30, if you see. So that is on the left hand side you have the strain tensor form, that is the sigma ij deva f by deva sigma ij, and that would become the summation of all those equations obtained from the 6 terms obtained equations from 29. So it is summation of capital F and the square of this term, first term, then capital G square of the difference of these terms in between, and then capital H square of the difference of these terms plus twice capital L sigma yz square plus twice capital M sigma zx square plus twice n sigma xy square, and that this sum would be equal to 1. And please note that symmetry, that is the sigma xy is equal to sigma yz etc. So if we remove the symmetry and then it is written as, that is dw is equal to sigma ij deva f deva sigma ij d lambda, it becomes equal to d lambda, and that is sigma ij d sigma ij, it becomes the generalized stress multiplied in increment, and it is nothing but equal to d lambda. The choice of one generalized quantity is therefore arbitrary, and choosing the generalized yield stress, if we choose, so it can be written as sigma bar, which is generalized yield stress, and it can be written here as shown this one. So it has again 6 term and it is shown here in like under root 3 by 2 and summation within the long summation here within larger bracket, and then it has inside the 4 components. So, the first component has capital F multiplied by square of the difference of the term like sigma yy minus sigma zz plus capital G square of the difference of the component stress component like sigma zx minus sigma xx plus capital H square of the stress component like direct stress component like sigma xx minus sigma yy plus shear component as 2 capital L sigma yz square plus 2 capital M sigma zx square plus 2 capital N sigma xy square, and all these together has to be multiplied by 1 by capital G plus capital F plus capital H, and this is what is in within its square root, and that can be simply written as this generalized stress is equal to under root 3 by 2 and in bracket in under root the summation, the 3 summation of the constant capital F, capital G and capital H. So, if you use the equation number 30 and one can have the choice of the above expression is such that the under the condition of vanishing anisotropy it will reduce to a 1 Mises generalized stress, that is sigma bar for isotropic material. So, and that would be a check also. So, the corresponding generalized strain increment, that is d epsilon bar, can now be put this in the form of equation 34. That means it becomes equal to d lambda by simply the generalized stress. So, from equation 32, if you substitute now this particular value of d lambda which is derived in equation 32 and the value of sigma, one can get using the equation 27 as well as equation 33, one can get the strain, generalized strain increment as this one. So, that becomes under root 3 by 2 and in bracket in under root the summation of the 3 constant terms at capital S, capital G and capital H and multiplied by d lambda. This can further be, if you substitute the value of d lambda from equation number 32. So, we get this long term which has 1, 2, 3, 4, 5, 6 term. So, this is shown here in equation number 35. So, this equation number 35 it is a, one can further extend it. So, it is a long, you see this very carefully. So, the strain increment, generalized strain increment, you have now the terms like capital F, capital G, capital H, capital Q, capital L, capital M, capital N and the corresponding the strain increment, including the direct strain increment and shear component of the strain increment. So, this equation 35, if now you use equation 33 and 35, this particular equation can be written further in a very simplified manner which is shown here in equation 36. That means it becomes the d epsilon bar divided by sigma bar, that is the generalized form. It will be simply equal to under root of the numerator and the under root in the denominator as. So, numerator it comes out to be 2 by 3 multiplied by capital S, F, capital G, capital H. On the denominator side it is under root 3 by 2 which is corresponding to the strain increment, and that is 3 by 2 multiplied by capital F, capital G, capital H. This is all in under root and multiplied by the factor d lambda, and therefore d lambda can be obtained. So, d lambda becomes 3 by 2 multiplied by 1 by capital F, capital G, capital H, and then multiplied by d epsilon generalized divided by generalized stress. So, one can now write down the flow rule and it can be written here. This flow rule where all the terms, if you substitute from equation 30 in, that is the d lambda value, if you substitute, so it becomes, that means d epsilon x zz r xx or we can write. So, for an example, d epsilon xx divided by capital A xx equal to d epsilon yy divided by capital A yy, and it is d epsilon zz divided by capital A zz is equal to d epsilon xy divided by capital A xy, and it is equal to d yz divided by capital A yz, and is equal to d epsilon zx is divided by capital A zx, and this is whole together would become 3 by 2 multiplied by 1 by capital F, capital G, capital H, multiplied by simply generalized strain increment divided by generalized stress, and that is what is equal to d lambda. So, this forms the basis of the equation number 38 is the flow rule associated with anisotropic Hills. So, and because it is correct as well, one can check it. If you substitute the value of the components F, G, H and L, M, N all correspondingly to isotropic, we get the direct one message. That means it is correct. This yield criteria is very popular, especially when we model the sheet forming problems like sheet metal rolling, cup forming and other operations, and anisotropy becomes very important. Even scientists in metallurgy are more concerned. So, the alloy development for the sheet materials, it concerned and it looks the anisotropy, and it is assumed that the anisotropy, if it is there, because one cannot completely remove these, so at least it should be within control. So, the proper forming parameters could be selected in the best way, so that the good forming failure. This is what the whole details about the anisotropic Hills yield criteria therefore, and one can have. So, I would again like to thank you for your patience, listening very patiently, and hopefully you will give your feedback and suggestion so that we can improve. So, back all those analysis in especially the yield criteria and just correlate with this lecture. Thank you all. Thank you once again. Thank you.